In this video, we're going to be looking at solving problems when there are no numbers given to you. So these are typically calculation style problems, except the variables aren't directly given to you. So an example of a problem might look something like this, where it asks you, how does the amount of work change when you push an object double the distance? Remember that a push is a force, which helps us because we know that our equation is for work equals force times distance. So the way we set these up, or the way that I like to set them up, is I write out our equation like I just did, and then I draw a dotted line down the middle here. And what we're going to do is attack the variable that's changing. So how does the amount of work change when you push an object double the distance? Well, it doesn't say anything about changing the force because there's nothing about changing how we push. We're only doubling the distance. Now, mathematically, when you double the distance, doubling is multiplying by 2. So we're going to end up multiplying the distance, by 2. If you think back to your rules for algebra, anything that you do to the right side of the equation, you also have to do to the left side of the equation. So when we double the distance, we are also going to be doubling or multiplying the amount of work we do 2 times. Here's another example problem asking, how does the power of an engine change when you double the amount of work done in the same amount of time? So we're going to be looking at power, doubling the amount of work, so we know there's work, and time. So our equation that we use for this is power equals work divided by time. We can draw our dotted line here. So once again, we're looking at a situation where we're doubling, and we're doubling the work without changing the time. So the work is going to be doubled. It's multiplying by 2. I'm going to go ahead and draw in our fraction bar there so we know if we're affecting the numerator or the denominator. So when we multiply the numerator on the right by 2, we have to do the same thing to the left side. So we multiplied by 2 there, and we're going to multiply by 2 here. So doubling the amount of work done in the same amount of time is going to increase our power 2 times, or double our power. Another very similar problem, we're going to asking, how does the power of an engine change? However, this time we're doubling the time without changing the work. So writing out our equation, we have power equals work divided by time. Draw our dotted line. This time, though, we're not affecting the work, we're doubling the time. So times 2, but I'm going to put it in the denominator. Now, remember that this represents a fraction. So if I put my 1 over here, okay, because remember a fraction has to have some type of numerator, in this case 1, the end result when we double the time is that we're going to be multiplying the left side of the equation times 1/2. So if we double the time that it takes, we're decreasing the power by 1/2. Another way of saying that is that we can do half the work in the same amount of time, or that it takes us 2 times the amount of time to do the same amount of work. Here we're looking at gravitational potential energy and how it's affected when we double the height and when we triple the mass of the object. So just like before, we're going to write out our equation. Gravitational potential energy is equal to the mass times the acceleration of gravity times the height. I'll put in some small little multiplication symbols there if I can. Times and times. Draw my dotted line. When we double the height, we're multiplying it times 2. And when we triple the mass, we are going to be multiplying it times 3. Now we've got 2 different things that are going on the right side of the equation. We have a times 3 and a times 2. Well, what we need to do is find the product of these 2 things. So we're going to multiply them together, and we end up with a times 6. So what that means is we've now multiplied the right side of our equation times 6. We need to do the same thing to the left side of our equation times 6. So we doubled the height, we tripled the mass. The end result, our product, was times 6, so we have increased the gravitational potential energy 6 times what it originally was. In this problem, we're asked what happens to the kinetic energy if we double the speed. So our equation for kinetic energy is kinetic energy, Ke equals 1/2 equals mv squared, mass times velocity squared. It doesn't say velocity anywhere in the problem. Remember that velocity is speed with a direction. So this speed, what we're referring to, is we're going to be changing the velocity. Draw in our dotted line here. Changing the velocity, we are going to go down from velocity. Doubling, we said, is multiplying by 2, so it's 2 times. But you'll notice that there is a square here. The velocity is squared. So whatever we do to the velocity, we also have to take into account this square there. So times 2 squared. 2 squared is 2 times 2, which is times 4. All right, so times 4 is the end result of what we have done to the right side of the equation. Whatever we do to the right side, we got to do to the left. So times 4. So you'll notice when we have velocity in this equation, because of this square, any change in velocity will have a much greater effect than changing kinetic to the change in kinetic energy. If we had just doubled the mass, we would have ended up multiplying this times 2. So a change in velocity will produce a much greater change in kinetic energy.